start off the electrochemistry chapter, it's helpful to review some information from first semester general chemistry on redox reactions. So the important part we have to remember, first off, we have oil rig, or whatever acronym you want to use. So reactions where oxidation happens, what happens is, our oil rig part, is this is a loss of electrons. Whereas our rig part, our reduction reactions are going to be ones where we gain electrons. So that means we're looking at reactions where electrons move around. So if no electrons change, then we don't have an oxidation reaction. But we need to have a tool to be able to identify, did the electrons on the left side, or reactants, change when they went to the product side on the right side? So to do this, we apply something we call redox numbers to each of our atoms and ions in our chemical equation, and we compare the reactant and product side, and we see, do the numbers change? If so, that can be used to designate did it lose or gain electrons, or if they stay the same, that atom didn't change any. And if all the atoms stay the same, then we don't have a redox reaction. On the other hand, if you have some change, you're going to have some that go from that become more positive and some that become more negative, because if the electrons leave one atom, they have to go to another. So you're not going to have a case where you have just oxidation or just reduction. Somehow you're going to have your electrons going somewhere. They can't just disappear, or they can't just appear from nowhere. To assign these numbers, we have a set of rules we use. I promise the next slide we'll be reviewing it. So if you don't remember these, what might be helpful is I'm going to go over these. Try using these rules on our next examples. With these rules, we do have to apply them in a specific order. The reason for this is some of the atoms we come up here with, we actually won't be able to use the rule. And we'll show you when that comes up as an example, because it's the last atom in our compound. And so all the other atoms end up determining what value we give for it. And I'll show you how that comes up. So first, if you have an element by itself, it has an oxidation state of 0. So for example, if I have a sodium atom by itself in the solid form, we have an oxidation state of 0. That's the first rule you apply. It's the easiest thing to do. In problems, these are great to look for. You're just like, hey, that thing is by itself, it's a 0. This also occurs if we have an atom bonded to itself. So for example, if you have O2 as a gas, we're going to assign it an oxidation state of 0. Rule 2, monoatomic ions have an oxidation state equal to their charge. So for example, if you have Fe, 3+, aqueous, we say it has an oxidation state of +3. Those are very easy. The third, the sum of the oxidation states of all the atoms in a compound, note we're not saying polyatomic ion, but a compound, is 0. For example, if you have water, H2O, we're going to learn some rules later about how we can assign oxygen to a -2 and hydrogen to a +1. So since there are 2 +1s and a -2, that overall gives you a value of 0. This is the rule we will use that causes us to sometimes change one of the atoms. And you'll see that when it comes up, because we keep assigning atoms in our compound till we get down to one unassigned atom. We then have to use this rule because this rule is really high up. So if you end up assigning an atom to a value and you only have one left, you quit using the rest of the rules and you go up to this rule. And we'll show that example when we get to, let's say, over here. When we get to near the bottom rule and we get to fluorine, I'll show where this comes up. Now, if you instead have a polyatomic ion, some of the oxidation states are equal to the value of the charge on that ion. So for example, let's say we had NO3-, one of our polyatomic ions. We're going to learn in a second, this nitrogen is going to be assigned an oxidation state of -2. I didn't give myself enough room to write it. And so 3 oxygens means this will be -6. And since it's a -1 value you're trying to get to, this nitrogen will be +5. Because +5 minus 6 gives a -1 overall value, which matches the polyatomic ion. Our next rule is group 1 metals have an oxidation state of +1 in all of their compounds, and group 2 metals have an oxidation state of +2. That's things like sodium, calcium, stuff like that. Our last rule is the one you will probably use the most. Assign nonmetals based on the table to the right, and do them in order. So fluorine is a -1, hydrogen's a +1, oxygen's a -2. Then we have group 7, 6, and 5As, where group 7A is stuff like fluorine, bromine, iodine, your halogens. Group 6A is the one that starts with oxygen, so like oxygen and sulfur, and then group 5A is what we have starting with nitrogen. Now to show you an example of, I said sometimes when you assign those, you won't actually give these values. So an example of this is the molecule OF2. So you'll notice if I go down the list of rules before the table, none of these rules cover it because there's not a metal there. So my oxidation state rules say I put a -1 on fluorine. Well, now I only have one atom left. So even though the table right here says oxygen will be -2, this is my last remaining atom. When I get to the last remaining atom, I have to go to the rule I start, over here, which is the sum of the oxidation of all the atoms in a compound is 0. So since fluorine has an oxidation state of -1, this is a -2 overall, so to balance it, this needs to be a +2. So we assign these in order until we get to the last atom. And then we have to assign it based on the compound being 0, or for a polyatomic ion, the oxidation state should add up to the charge of the polyatomic ion. Let's look at some examples, because I know I said a bunch of words, and just trying to look at those is not the easiest, and what might help is after you try the examples, you might go back to some of these if you need to. So let's practice these. I want you to give this a try. Try doing both problems, and if you don't remember what an oxidizing agent or a reducing agent is, I'll go over that when going over the problem, but try to at least assign the values of the oxidation states, and if you can figure out which ones change, that's good too. Let's look at these. So, HBr. For assigning our rules, if we go back, you'll notice hydrogen is the first rule we come to at +1, so it will be a value of +1. Then to get the molecule overall to 0, bromine will be a -1. Again in CH4, hydrogen's a +1. There are 4 of them, so since we have a +4 overall, this carbon needs to be a -4 to balance that out. We then get to carbon monoxide. When we assign our rules, oxygen's a -2. To balance that -2, since there's only one oxygen, this would be a +2. Note, if you would, we'll do CO2 in a second, so I won't worry about that note. We'll be seeing it in a second. So we get to Fe2O3. Iron is not a group 1 or group 2 metal, so our rules don't answer that. It doesn't have to be a +1 or a +2. So we get to oxygen. It's the first rule that comes up. It's a -2. There are 3 oxygens. That gives us an oxidation state of -6. We should be getting to an overall at 0 for a neutral compound. So to make iron balance a -6, each iron needs to be a +3. Since there are 2 of them, 2 times 3 is +6, and 3 times -2 is -6. So they add up in total to 0. Now let's do those same things now with this reaction. We have to assign all the oxidation states first, and then we look for which one changes between the reactant and the product side. So some of these molecules we've already done. So this is a +3, this is a -2, this is a +2, this is a -2. As a side note, you'll notice I'm not worried about these coefficients here. They're not going to change the individual oxidation states. Now iron as a solid is by itself, so it's a value of 0. Carbon dioxide, we assign oxygen first, -2. There are 2 of them, that gives a value of -4. That means this carbon has to be a +4. So our first questions are what is oxidized and what is reduced. So for those questions, we want to see what changes. So remember, oxidation is loss. So which atom lost electrons? So if we go and we look through these cases, what we'll see is that the carbon changes from +2 on the left side to +4 on the product side. Since it goes from +2 to +4, it had to lose 2 electrons. Since electrons are negative, as they lose them, the atom will get more positive. So for our oxidation, that's going to be carbon as it went from +2 to +4, which was a loss. Now if we look for our reduction, that's going to be something that gained. That's gain of electrons. So here, our iron went from +3 to 0. So if it's gaining electrons, remember electrons are negatively charged. So they're negative values. So if it's gaining negatives, it would go from +3 to 0. It's actually gaining 3 negative values. So it gained 3 electrons in the process because it went from +3 to 0. So that is a gain of electrons. And I'll note that can, I know, sometimes give people a hard time at first because it's becoming more negative, but that means gain since electrons are negative. We've got 2 other questions. What's the oxidizing agent, and what's the reducing agent? The way to think of these is the oxidizing agent is the thing that causes something else to be oxidized. So in this case, carbon was oxidized. So what compound in our reactant side caused that to happen? Well, that was the Fe2O3, because it's the iron that's being reduced. So by adding Fe2O3 in this case, our iron 3 oxide, it's able to cause something else to be oxidized. So our oxidizing agent would be Fe2O3. So OA, oxidizing agent. Our reducing agent is the thing that caused something else to be reduced. So in this case, the iron atom in iron 3 oxide is reduced. The carbon monoxide is what's doing that, so we would say that the carbon monoxide was our reducing agent. You'll also notice that in each of these cases, I mention a reactant, since we're talking about what is happening when we combine these that causes oxidation or reduction, so it's something we put into the initial reaction that causes something else to have that change. So our oxidizing agent is a reactant that caused something else to be oxidized, which means it itself was reduced. Whereas our reducing agent is something that caused something else to be reduced, so it was oxidized. The reason we can say this in this way is because with oxidation being loss of electrons and reduction being gain of electrons, whatever loses causes something else to gain. Whereas when one thing gains, it causes something else to lose. That's the end of our review on redox reactions. We will now use this to do some electrochemistry examples coming up.